I'll go to the next page. Okay. What I'm going to do is we are going to remove the support at C. Okay, I'm going to do the complete opposite. Okay, we're going to do the complete opposite. Okay, so remember what I told you guys, it can be confusing, right? If I remove the support C, whether is it tension or compression. Okay, so in normal time, what I'll do, I'll print this on a piece of paper and I'll rotate it, but I can't do that on a computer. So I'm going into I don't think I can flip this image in this software. Oh, I can. Ooh, okay. So I'm going to copy. I'm going to paste. I'm going to rotate this right by 90 degrees. Okay, now I have a better image on what is going on. Okay, so we are going to I'm going to put over here. Okay, we are going to remove the support at point C. Okay, we are going to remove the support at point C. So now it's easier to visualize, right? I'm going to remove the support at point C. Okay, so step one. I think this example will go on for like your break will be like 10:35. Okay, bear with me. Okay, so step one. Okay, so this is our step one. So we know that we have to divide this into into three. Okay, not four. Okay, so this is one. So we divide this. This is because change of material, change of cross-sectional area, and because of the applied load. Okay, and this is 2, and this is 3. Okay, so we are going to calculate. So if you look at the hangman theory, okay, load of section 1. Okay, so before we do that, I just remind you that we're going to apply deflection is equal to PL over AE, right? Positive is tensile, negative is compression. I'm just writing you because I'm teaching. When you do your exam or your test, you don't need to write this, okay? So that's the notation that we're going to use, okay? So now we have minus, okay, we have minus twice, okay, 75 times 10 power 3. Because on section 1, the 75 is going to induce a compression. And then plus by twice, the 100 is going to induce a tensile. Okay. So that is my force. The things about the forces, okay. Then the length is equal to 0.25. Okay. And then the cross-sectional area, we are given the diameter, so the cross-sectional area is pi 0.025 squared. And AD, I do apologize for that. Okay, so AD, they mentioned that is made of what? AD or DA is made of brass. So if you look at the solution manual, the brass they use is 101. Okay, times 10 to the power 9. So this will be equal to minus 2 times 10 power 3 plus by 2 times 2, 100 power 3 times 5.25 divided by shift pi divided by 0.025 squared divided by 101 power 9. And I got positive, it's in tension, positive 63.032 times 10 to the power minus 6 meters. Okay. Then deflection due to the load at point 2 is equal to, so at section 2, it's not going to fill the 75 anymore. It's only going to fill the 200s or the two 100s. So positive is going to be tension. Now, if I have not rotated the diagram like this, I can be a bit confused also. Okay, so my sincere advice to you, if you get a question like that, just rotate the diagram or print it out and just rotate, you'll see better. Okay, it's all about the visualization. So pi, the cross-sectional area, the diameter is 20 millimeters, so the radius is 10 millimeters. Then I'm going to look at the solution manual. What is the Young's modulus? They use 200. Okay, I'm going to use 200 also. Okay, so this is equal to times 0.5 divided by shift pi divided by 0.01 squared divided by 200 power 9. I get 1.592 times 10 to the power minus 3 meters. Okay, so this is positive, and deflection at 0.3 is equal to, so there's no load. Okay, but I'll just put it down for you. Okay, 0.25 divided by pi 0.025 squared, and 101 is made of brass. Now the whole thing is equal to 0. Okay. So from here, we can calculate the deflection due to the load. Okay. So the deflection due to the load will be equal to 63.032 times 10 to the power minus 6 plus 1.592 times 10 to the power minus 3, okay, plus by 0. We add up them up. So 63.032 power minus 6 plus by 1.592 power minus 3 is equal to 1.655, positive 1.655 times 10 to the power minus 3 meters. Okay. Then we are going to calculate step 2, right? So we've done this. So step 2. Okay, step 2. Do you all urgently need a break now, or can I go on for 5 more minutes? It's your call. Anyone? Okay, if I don't hear anything, means carry on. So step 2 is we are going to place a redundant load. At point C. Now, when we place a down, again, this is a unique question, okay? So that's why you cannot take one example and link to the other. Now, what happened now is we decide to remove all the load, okay? So for this case, like what I told you, right? We are going to get rid of all this. So now we don't see all this load now, okay? Because we analyzed in step 1 already. Okay, we don't see all this load. Okay. Now, from this analysis down here, right, we realize that it's going into what? Tension, right? So we know that we have to push it back. Okay. So this is my reaction at point C. Okay. Now, if it happened that this is negative, right? In another case, if this is negative, then if we were given the entire structure, right, we calculate that the applied load is negative, then you have to, your RC will be in this direction to induce a what? A positive deflection. Okay. So for this case, it's in tensile. We know it's coming down. We push it back. In a different case, so this is different case. If the redundant load happen to be negative, okay, then your RC have to induce a what? Positive, or your redundant load at point C have to introduce a what? Positive deflection. Okay, this you have to remember. Okay, or it's part of the analysis. Okay, so but for this case, we know that the load is inducing a tensile. That's why I push my RC is going back up. Are we clear? Okay. So from here again, due to now this is purely due to geometry. Due to geometry, right? We again have to divide the section into 1, 2, and 3. Right. So for this case, how many sections to divide in the applied load and the redundant load is the same. In the previous example, it was not. Okay. So now we know that RC is going to induce a compression. Okay. All the section 1, 2, and 3 are going to feel RC. Okay. So now we calculate deflection due to the redundant load at section 1. So it's equal to minus RC, right? Multiplied by the length of 0.25. Then we have the area, which is equal to pi 0.025 squared, and this is brass. Okay, so this will be equal to 0.25 divided by 0.25 divided by shift pi divided by 0.025 squared divided by 101 power 9 is equal to 1.26 times 10 to the power 9. Okay, so it's going to be minus 1.261 RC, and then deflection of 0.2, again minus RC. The entire length is 0.5, right? Pi 0.01 squared, and then the Young's modulus is 200. So this is equal to 0.5 divided by shift pi divided by 0.01 squared divided by 200 power 9. I get 7.958 minus 7.958 times 10 to the power minus 9 RC, and finally the redundant load at 3. Okay, so minus RC multiplied by 0.25 is the same as the first section because geometry is all the same, material is the same. So this will be equal to minus 1.261 times 10 to the power minus 9 RC. Okay, so the summation of the deflection due to the redundant load, so you add all of them, so minus 1.261 10 power 9 RC minus 7.958 times 10 to the power minus 9 RC minus 1.261 times by 10 to the power minus 9 RC. So this will be equal to minus 1.261 power minus 9 minus 7.958 power minus 9 minus 1.261 power minus 9 is equal to minus 10.48. Almost done. Okay, so we have we're going to apply deflection of L plus by deflection of the redundant load is equal to 0. So the applied load is equal to what? 63, no, 1.655. Okay, 1.655 times 10 to the power minus 3, right? Plus by minus 10.48 times 10 to the power minus 9 RC is equal to 0. So therefore, the reaction of C is equal to 1.655 times 10 to the power minus 3 divided by 10.48 times 10 to the power minus 9. Your RC is equal to 1.655 power minus 3 divided by 10.48 power minus 9. So it's equal to 157.91 or 0.92 times 10 to the power 3 Newton, and it's going upwards. Okay. So let's remember 157.92. Okay. So this is the reaction at point C. So if you go back to the solution manual, okay, reaction of point C is 157.89. We get 92 is close enough. Okay, let's go for a break. Okay, and when we come back for a break, we calculate what is our FD equal to. It's not going to be too far. Let's go for a break, and we come back at let's come back at 10:55. How's that? Okay, let's come at 10.
Dr. Ishii, can you go to the previous slide and leave it on there, please?
I will.
Thank you.
Someone had a question. I will address the question after the break. I'm going to stop recording first, okay?